Perfect. Okay, so the title is the K-distribution of random graph C-star algebras.
Thank you, Piotr. And thank you to the organizers for giving me this opportunity to tell you about some joint work with my colleague, Igor Havkin, who's also in Prague. So the kind of broad question I'm interested in is, suppose you construct a C-star algebra in your favorite way, deductive limit or cross product, graph C-star algebra. But instead of making specific choices to get some structure that you want, you make random choices. And then the question is, all right, well, does my C-star algebra have structure I'm interested in? You ask, what's the likelihood that it has this kind of structure? So I haven't quite figured out what random cross products should be yet, but discussion for a different conference. As far as graph C-star algebras go, these are particularly well suited to this kind of question for a couple of reasons. I mean, first of all, there is already this very rich theory of random graphs, which we can use and interpret as far as the C-star algebras go. But also, we have this K-theoretic classification graph C-star algebra. So if we want to understand the kinds of algebras we get, it's enough to understand the kind of K-theory that we get. Right, and I'll explain as we go along exactly what I mean by this, but that's what the title means. All right, so we're going to construct some random graphs and then look at the K-theory that we get, essentially. All right. So here's a motivating problem, a specific motivating problem for today. Suppose that we construct a random graph. So we have a fixed set of vertices, 1 to n, which we should think of as being large. And then we randomly add some edges. Then the question is, what's the probability that we get a graph C-star algebra that is stably isomorphic to some Kunz algebra? That's what I mean by this this sort of notation. Oops. This notation here is just isomorphic up to tensoring with the compact operators. Right. So before we get into this, and before indeed I tell you exactly what I mean by randomly adding edges, anyone have any sort of instinct about the kind of answer to this question? Like maybe a ballpark estimate?
The Kunz algebra corresponds to a graph which has many loops around the same
exactly. Yeah,
vertex.
It's one vertex and many loops.
And tensoring by K. Just
so, as I will remind you, as far as the K-theoretic classification goes, you know that we're going to most of the time talking about just simple graph C-star algebras. So if you know that the K0 and K1 groups are the same, the graph algebras are stably isomorphic. If you also know where the position of the unit is, then you nail down isomorphism on the nose. So throughout the talk, I'm not really at all going to talk about this position of the unit. So I'm all the time asking about just this stable isomorphism. I'm just genuinely curious whether anyone has like some feeling, should this be like almost never or almost all of the time? But okay, we will see as we go along. Yeah, Jack has this.
Quite harebrained, I think, but if the matrix of the graph is invertible, then you should be getting like a Kunz algebra. And that's okay, these are integer matrices, but somehow if it's still generic, then that's
excellent observation. Excellent and very relevant observation. Okay, so let's get into it then. All right, so first of all, let me tell you exactly what I mean by randomly adding edges. So we're going to use 3 models of doing this random graph construction. The first is what I'll call the Bernoulli digraph model. So depending upon some probability Q that's between 0 and 1. And they're constructed like this. So for each ordered pair of edges, you toss a coin, possibly a biased coin. Heads, you draw an edge. Tails, you don't. Yeah, that's all I mean by this. So another way of thinking about this is you have, as Jack was sort of mentioning, the adjacency matrix is a random integer valued matrix. So each of the entries of this matrix is an independent Bernoulli random variable. So it has 1 with probability Q and 0 with probability 1 minus Q. Just a different way of describing this same thing I said about tossing a coin. Okay, so that's the first model of random graph. The second model is what I'll refer to as Erdős-Renyi graphs, ENQ, again, depending upon this probability Q. And these are just the undirected, in other words, the symmetric versions of the Bernoulli diagrams. So for the Bernoulli diagrams, I toss for I and J, I toss a coin for I to J to decide whether to draw an edge this way, and I toss it again to decide whether to draw an edge this way. Here, I just toss the coin once. Or equivalently, the adjacency matrix is symmetric. So we have these independent Bernoulli entries happening in the upper triangle, and then I just reflect. And the reason I'm calling these Erdős-Renyi graphs is because these are kinds of graphs were studied by Erdős and Renyi in the 50s, in particular in this starting paper on random graphs 1. A couple of differences on the kinds of graphs they study there. First of all, I am allowing loops. So for each vertex, you toss a coin to decide whether to draw a loop. They did not.
Why? Can you say why?
Why they did not?
Yeah.
Well, so for one thing, I mean, typically I think the notion of a graph often refers to a sort of loopless graph without multi-edges. But also one of the primary questions they're interested in is whether or not this graph is connected probabilistically. And adding loops doesn't matter if you're interested in a question of connectivity. Okay. And the second thing is they don't quite use this model that I'm describing about for each pair of vertices you toss a coin. They use a slightly different but very related model. So for each integer m, which tells you how many edges there are, so there are a certain collection of graphs on n labeled vertices with exactly m edges, undirected graphs, and you just choose one of them with equal probability. So it's a slightly different model, but they are very closely related, and there are ways of going back and forth between the two, and from statements about one, you can deduce statements about the other. Okay, so the theorem due to Erdős and Renyi is the following, as far as connectivity goes. So let's say this Q, with the probability Q in general can depend on n. And let's suppose it has the following form. So it's log n plus some function omega, all divided by n. And then depending upon the asymptotic behavior of this omega, that tells you about the asymptotic probability of getting something connected. So if this omega is going off to positive infinity, that means the probability of adding edges is growing and growing and growing. Then with probability 1 as n tends to infinity, you get something connected. On the flip side of this, if omega is going down to minus infinity, then with probabilities 1 as n goes to infinity, you get something that's almost never connected. And in between, if omega goes to some value c, some constant c, then the connectivity probability is e to the minus c. So I'm not going to get into how to prove this. So throughout the talk, I'm going to be telling you about various just incredible results from random graph theory and random matrix theory that most of the time we're just going to treat as a bit of magic as far as we're concerned. Right? Here's one bit of magic. So an immediate corollary of this. So this is for the undirected, the symmetric version. So from this, you can immediately deduce a corresponding result for the directed version. So the Bernoulli digraph version, remember, that's just the undirected version of the Erdős-Renyi one. You can think of it like this. So I have my n vertices. I put an Erdős-Renyi graph, a random one, on these vertices, describing the connectivity in the sort of upper triangular. So for I, so j bigger than or equal to I. And then I just overlay that another Erdős-Renyi graph to describe the ones below. So j less than I, right? And then strong connectivity of this directed graph is, in other words, just asking for connectivity of both of these graphs simultaneously. All right, so the probabilities you get are just then the squares of the probabilities that we had previously. So 0 squared is 0, e to the minus c squared is e to the minus 2, e to the minus c, and 1 squared is 1. Okay, so in both of these cases, we have this statement about connectivity. By the way,
sorry, could you draw a connected graph which is not strongly connected?
Yeah, sure. I mean, just two vertices, and then a arrow from 1 to 2.
But not from 2 to 1.
But not from 2 to 1. Connected, but not strictly. Yeah, maybe I should clarify. By strongly connected, I mean for every I and for every j, there is some path from I to j. By the way, so here I have this expression for q. It's log n plus omega over n. So in particular, if q is constant, that means, let's say a half. That means this omega is like n over 2 minus log n. So it's going off to infinity. So if q is kept constant, then we are in the last condition. So asymptotic, so with probabilities approaching 1 as n tends to infinity, we get something strongly connected. All right. So that means we can immediately say something about the graph C-star algebras that you get. So it's combining results that are, I suppose, well known to those who study graph algebras. If we have a graph that is strongly connected, I should also mention that you almost never get a graph that is just a single cycle. That's like if you have this big random matrix and you're just getting a permutation matrix, that it's extremely unlikely. Okay, so we're getting something that's strongly connected, not a single cycle. So you get a purely infinite simple C-star algebra. And it's I've described it as a simple Kunz-Krieger algebra. One way of thinking about Kunz-Krieger algebra, it's the graph algebra of a finite graph without sinks. Okay, so that's the kind of graph that we're getting. By the way, so I keep all the time saying with probability tending to 1 as n tends to infinity, very long-winded. This is some shorthand for saying something like this. So if you have a sequence of events, you say that it happens asymptotically almost surely, AAS. Oh, I have this highlighting thing. So AAS, or with high probability, this synonyms with high probability. And this, it just means this statement that the probability tends to 1 as n tends to infinity. So asymptotically, almost surely, we get a simple Kunz-Krieger algebra by this random graph process. All right, and what we know about such algebras is that they are classifiable by K-theory, just the K0 group, the K1 group, and the position of the unit, if you're interested in on-the-nose isomorphism as opposed to stable isomorphism. So that you can appeal to the Kirchberg-Phillips classification of a purely infinite simple C-star algebras for this, or indeed by Michael Roerdam's earlier classification of simple Kunz-Krieger algebra. Let me just remind you what the K-theory of a finite graph without sinks is. So if we take the adjacency matrix and we take the transpose and we subtract the identity, then the K0 group is the co-kernel of this matrix. And the K1 group is the kernel. Or another way of seeing the K1 group is the torsion-free part of K0. So K0 is going to be some finite abelian, finitely generated abelian group, sorry. There's going to have some free part and then some direct sum of cyclic groups. So the free part is the K1 group. So that's why I said here that these graphs are classifiable by the K0 group. If you know the K0 group, then you know what the torsion free part is, so you know the K1 group. Okay, so before I start telling you about some more about the K-theory, let me tell you about the third. So I said there'll be 3 different kinds of random graph models. Here's the third kind. And here AAS is this asymptotic, almost sure. So these graphs also have this connectivity, and so they will also, with high probability, give you a classifiable C-star algebra. And these are regular multigraphs. So I'll denote them like this: G and R. So here n is meant to be an even natural number, and R is meant to be an integer bigger than or equal to 3. And they are constructed like this. So I take a perfect matching on the set of n vertices. So, okay, so let's say there are n of you, let's say an even number n of you. I pair you together at random. And then I do that again. And then I do that again. And I do that R times. And then I keep track of the pairings by drawing a graph. That's how I build this graph model. So here's an example picture. So here we have 6 vertices. So in the first round of pairings, I pair together, 1 and 2, 3 and 4, 5 and 6. And then in the second round of pairings, I pair together 2 and 3, 1 and 5, and 4 and 6. Then in the third round, I pair together 3 and 3 and 5, 2 and 6, and 1 and 4. And I just keep track of everything by drawing some edges. This will give you an undirected graph, but I just make it a directed one symmetrically. So I place each edge by 2 edges, one going from I to J, one going from J to I. By the way, so the reason I want R to be bigger than or equal to 3 is so that I do get, with high probability, a connected graph. That's actually, so the ones for the Erdős-Renyi result was quite a deep result. I mean, this is actually not so hard to show for this. So it's a few lines of argument to show that these are with high probability connected.
So multigraph means that you have colors, right?
Right. Sorry. A good question. By multigraph, I just mean that I'm allowing repeated edges. So it didn't happen in this example, but in this procedure where I'm pairing you together, it could happen that I paired with the same person more than once. And in that case, I'll have more than one edge between 2 vertices. That's what I mean by multigraph. So the other 2 graphs were not. I have at most one edge, but here I can have potentially even R edges between 2 vertices. Okay, so again, the adjacency matrix that I get is symmetric. So I have the lower ones are the same as the upper ones, but the entries in the upper triangle are not independent. So unlike the Erdős-Renyi graphs, because in particular, each row has to sum to R, so they can't be independent. Okay, so I'm choosing a very particular model of constructing an R regular graph. R is the regularity degree here via this perfect matching. There are other ways you could do it. So for example, you could just, similar to like the Erdős-Renyi situation, I could instead consider all possible graphs on n labeled vertices that are regular, allowing multiple edges but not loops. And then I choose one of those with equal probability. This will give you a different distribution, but it'll give you what's called a contiguous distribution. So in random graph theory, contiguity means the following. It means that if you have a sequence of events that occurs asymptotically almost surely for one distribution, then they also occur asymptotically almost surely for the other distribution. And this, what I just described, this what you might call the uniform model, where you list up all the possibilities and choose one with equal probability, is contiguous to this model that I described, the perfect matching model. Okay, so with this uniform model, you will also get with high probability connectivity. Okay, so let's get to what we can say about the K theory. And then now we get to the comment that Jack was making about we would expect that if n is very large, then you'd be very unlucky to get a matrix that's singular. So let's imagine that we have not integer valued matrices, but complex valued matrices varying with some continuous distribution. Then it's a very easy argument to see that with probability 1, you essentially get something non-singular. Okay, because all right, like the first n-1 columns of the matrix, they span at most an n-1 dimensional hyperspace in Cn. Okay, so for dependence, you need this one to be in the, let's say, linear span of this, and the measure of an n-1 dimensional space in n-dimensional space is 0. Okay, so that's why with probability 0, you're getting something singular. But if we have integer valued matrices, it's a much more difficult problem. And so difficult. So here I'm just saying what I was just saying, that so the expectation we would have, even in the case of integer matrices, is that if we have a very large integer valued matrix, then with probability approaching 1, we should get something non-singular. So this has been studied by many people over the years, including some heavy hitters. We have just listed a few here. So I think the first kind of positive result was by Komlosh in the 60s, and there I think he was considering 0-1 valued matrices, where you have they're each independent, and he was able to provide some bound that goes to 0 for the matrix being singular. And then later on by Khan, Komlosh, and Semeredi, and by Tao and Wu, so some Abel Prize and Fields Medal winners have worked on this. So for the kinds of random graph models that I've described, the Bernoulli, Edershreni, and these regular ones, I'm going to appeal to some results of Melanie Matchett-Wood, who's at Harvard, and some various of her co-authors, to deduce that in each of these cases, we know with high probability that the adjacency matrix is non-singular. And it's in fact, the results that they prove are general enough that, okay, certainly taking the transpose doesn't matter, affect the question of singularity, but subtracting the identity in principle might. It shouldn't, you might expect, and it doesn't. So the results that they prove are sufficiently general that subtracting the identity doesn't affect their probability estimates for non-singularity. Okay, so you remember the K1 group of our graph algebra is the kernel of this matrix Mn. So if this matrix is non-singular, that means that the K1 group is trivial. So with high probability, we are getting not just classifiable simple graph C-star algebras, but the K1 group is vanishing. So we really need to really just look at this K0 group, which will now be a finite abelian group. So that's how we're going to decide isomorphism. Before I get into the behavior of the K0 group, we can already from this provide a kind of intermediate answer to the question. So the question at the beginning I posed was, what's the probability of getting a Kunz algebra of the stable isomorphism? Well, now that we know that the K1 group is trivial, we can get with high probability not a Kunz algebra, but what I'll call a Kunz polygon. So Kunz polygon is a certain finite graph. This is terminology that I invented. I mean, you see why I'm calling this in a second. So okay, we've got these the vertex set n of n vertices. And I have these edges. So these L's are loops at each of the vertices. And these other edges, these EIJs, they are just going to be cycling around the n vertices with the multiplicities of each edge given by this tuple M, a tuple of natural numbers, an n tuple of natural numbers, which a natural number is not 0 in this definition. So here's a picture. By the way, before the picture, so the C-star algebra of such a graph, I'll call a Kunz polygon. So here's a picture. So on the left here, this is a Kunz hexagon. Okay, so I have 6 vertices. At each of the vertices, I have one loop, and then I have these EIJ edges just going from 1 to 2, 2 to 3, et cetera, looking around, and with multiplicities. So here the M1 is the multiplicity of this edge, the multiplicity of this edge, et cetera, et cetera. Okay, why am I defining it like this? It's just so that I get the right K theory, essentially. So first of all, this is it's a strongly connected graph with not a single cycle. So it is a Kunz-Krieger algebra. And by construction, the adjacency matrix is, so first of all, we have the identity matrix given by the loops. And then for the rest of the edges, it's just going to be some permutation of the diagonal matrix. Okay, so M2, because I have M2 edges going from 1 to 2. So that's in position 1, 2 of the matrix. Okay, and then just etc. going all the way down. So it's just some cyclic permutation of the diagonal matrix. So if I subtract the identity and I take the transpose, I get this diagonal matrix just with of the permutation. So in particular, the kernel and the co-kernel of this matrix is what I called Mn previously, is the same as the kernel and the co-kernel of the diagonal matrix. that's why I want the m's to be non-zero. So the kernel is 0 then. So I have trivial K1 for these graphs. And the K0 group is just going to be the direct sum of cyclic groups. So it's going to be Z mod M1Z plus Z mod M2Z plus blah, 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 blah. Okay, so it's going to have trivial K1 and some finite abelian K0. Okay, so here's some properties about these polygons. First of all, a Kunz one-gon is a Kunz algebra. So if I have a Kunz one-gon, that means I have one vertex, I have this loop L, and then I have M other loops. Okay, so that means if I have M plus 1 total loops, and that's the Kunz algebra, that's the graph of the Kunz algebra over M plus 1. So I'm calling it a Kunz polygon for these two reasons. In the case of n equals 1, I get a Kunz algebra, and in general, the graph looks like a polygon. But it's a generalization of a Kunz algebra in the following sense. So the K1 group is 0, just like Kunz algebras, but for Kunz algebras, the K0 group has to be something cyclic. If I have n loops, the K0 group is Z mod n minus 1 Z. But here, as I said, I get this finite direct sum of cyclic groups. So in principle, depending on how I choose the m's, it can be anything. It can be any finite abelian group is possible. So it's a generalization of a Kunz algebra where I'm allowing the K0 group to be any finite abelian group. Okay, so now let's get to the question of, we're trying to answer this question posed at the beginning. When do we get actually a Kunz algebra? So as I said, Kunz algebra, the K0 is cyclic. So the question is, when is this K0 group actually cyclic? Okay. Okay, so when is this K0 group cyclic? So first of all, by something like the Chinese remainder theorem or something we talked about to undergraduate days, this is cyclic precisely when these MIs are pairwise co-prime. Another way of thinking about this is that the Silov P subgroups of K0 are cyclic for every prime P. All right, in case it's been a while since undergrad, or you haven't thought about these in a while, let me just remind you what a Silov P subgroup is. Remember the Silov P subgroup of a group G, it's the maximal P subgroup of G. So it's the maximal group where every element is order some power of P. And if we have a finite abelian group presented in this canonical way, then it's easy to pick out the Silov subgroup. So here's just a couple of examples. So here I have this Silov 3 subgroup, which I'll denote by G3, and here I have this Silov 7 subgroup. So the Silov 3 subgroup here is non-cyclic, and that means that the group itself altogether is non-cyclic. And all the other Silov subgroups of this one are trivial. On the other hand, with this other one, I have a direct sum of two cyclic Silov subgroups, so the result is cyclic. I can just combine together the okay, just a brief reminder about what I mean by Silov subgroup. Okay, so and the last property of these Kunz polygons is that, all right, remember, we know that for our random graph models, we, with high probability, get something classifiable. And on the other hand, these Kunz polygons, they exhaust the range of the possible classifying invariants, as long as we know that K1 is 0. So with probability 1, so with high probability, we get something at least stably isomorphic to a Kunz polygon. Okay, so this is a kind of intermediate answer to the question I posed at the beginning. All right, so now to actually start to answer the question about the Kunz algebras, in other words, we need to just decide, see if we can figure out when is the K0 group actually cyclic. Okay, so that's what we've reduced the question to. Okay, so let's have a bit of a heuristic argument for the kinds of quantities, the kinds of probabilities that might come up in the answer to this question. When do we get something cyclic? So, and we're interested in the asymptotic probabilities, n goes to infinity. So as I mentioned, the probability of getting something cyclic is, in other words, all of the Silov subgroups should be cyclic. Remember, that's what I mean by the sub P. I'm talking about the Silov P subgroup. Okay, so here comes the heuristic part. Maybe it's reasonable to expect that the events of the different Silov subgroups being cyclic are independent. Maybe cyclicity of the 2 subgroup doesn't affect cyclicity of the 137 subgroup, right? Maybe this is a reasonable thing to expect. In that case, this probability that for all of them being cyclic is just the product over all primes of each of them being cyclic. And then maybe it's reasonable to swap these limits. So I have one limit as n goes to infinity, one infinite product over all primes, and maybe I can swap them. Okay. In that case, the kind of thing I should be looking for is this, what I'm calling CP. So it's the probability for a fixed prime P that asymptotically we get a cyclic Silov P subgroup. So adapting work, just incredible, some of this magic of Melanie Marchett-Wood and her authors, in particular, Nguyen. This quantity CP, cyclicity of a Silov P subgroup, is known in each of these 3 random graph models that I told you about. There's a slight caveat here for the last one, these GNRs, that if P is either 2 or P is an odd prime that divides R minus 1, there is no current theory about what the Silov P subgroup behavior should be. Let me just briefly explain why that is. So, okay, if we have a regular graph, that means that every row sums to 1. Sums to R, sorry. Exactly R entries that take the value 1. So if we subtract the identity, that means that each row sums to R minus 1. So that means that if P is a prime dividing R minus 1, then its matrix is singular mod P. So there is some kernel mod P, and that kernel mod P will contribute something non-trivial to the co-kernel mod P. Okay, so so whereas if P is co-prime to R minus 1, it's possible you could get a trivial P Silov subgroup. It's never the case if P divides R minus 1 that you get something trivial. There will always be some non-trivial factor. So that's as far as P dividing R minus 1. For P equals to 2, okay, let me just say briefly something about this magic. So Wood has this incredibly powerful kind of universal machinery for computing these kinds of distributions. Roughly speaking, if you have some random abelian groups and you know the moments of the distribution of these groups in a suitable sense, then you know what the distribution is. And the reason indeed that you get the same, so we'll see that in fact for these ENQs and these GNRs, you get the same distribution. The reason you get the same distribution is because you get the same moments. You can compute the moments. But the kind of counting you need to do to compute these moments, it doesn't work in characteristic 2 for these regular graphs. And it's not just that the argument doesn't work and maybe another argument works. No, you really do genuinely get something different if P equals 2. I'll come back to that later. Anyway, so all of this is just why this caveat is there in the latter case. In the other 2 cases, we have independence. So there's no such condition to worry about. Okay, so here's the theorem. So first I'm stating this for the first model, the Bernoulli diagrams. So for any prime and for any finite abelian P group G, the asymptotic probability that the P Silov subgroup of the K0 group is isomorphic to G is this expression. It's this expression involving a product of an infinite product involving the prime P, and then divided by the size of the automorphism group of G. Okay, I mean, all right. This expression is what's called the Cohen-Lenstra heuristics. Back in the 80s, Cohen and Lenstra were interested in the sort of the class groups of quadratic number fields, and they made these heuristic observations from some data that they appeared to be distributed in a way that is inversely proportional to the size of the automorphism group. And they conjectured that this is what should be governing the distribution of the kinds of groups and number theory that they were interested in. I mean, the basic principle at play here is that the more complicated the automorphism group G is, the less likely it is to occur naturally. So this is what they made this conjecture back in the 80s, and then 30 years later or so, Wood and various authors showed that proved that in various cases you actually do get this these Cohen-Lenstra heuristics, and here is one such case. Okay. So this is a statement for any finite abelian P group G, cyclic or not. So if we're interested in, so this CP, remember, is just the probability. So it's I'll just go back to the slide to tell you what CP was. It's the asymptotic probability that I get something cyclic. Okay, so this statement in A was for any finite abelian P group. Okay, so what are the cyclic ones? The trivial one, and Z mod PZ, and Z mod P squared Z, and Z mod P cubed Z. And we know what the size of the automorphism group of such a group Z mod P to the N Z. It's P to the N minus P to the N minus 1, then from undergraduate, whatever. So what you do is you just sum that expression 1 over P to the N minus P to the N minus 1 from N equals 1 to infinity, and you add in the plus 1 to give you the trivial one. Okay, and then there's a little bit, that's where the expression is coming from. That's it. This B is deduced from A just by inputting G to be all of the possible cyclic groups and summing them up. There's a little bit of analysis you need to do here, because we have this we have an infinite sum, and we have a limit, and you need to kind of swap them, but a suitable generalization of the big dominated convergence theorem will do this for you. I think there's something called the Vitali convergence theorem, if that rings a bell for you. That'll do it for you. So you're justified in just summing up this expression on the right. This gives you the cyclic probability. But what's really just incredible, I mean, it's just a beautiful piece of mathematics that they're actually able to prove this, is, and remember I said in this heuristic argument, maybe to determine the total probability of cyclic, of K0 being cyclic, we can just multiply together the probabilities of each prime individual being cyclic, and that'll be the answer. And that is the answer in this case. They managed to prove this. So it's this. So this expression in part C is just the product of this expression in part B over all primes, and it turns out to be about 85%. So that's the answer to the question posed at the beginning for these Bernoulli diagrams. 85%. If you give me a large set of vertices and I randomly add edges in this Bernoulli diagraph way, about 85% of the time I'll get a C-star algebra stably isomorphic to a Kunz algebra. Okay, I don't know about you, but I find this incredibly surprising. So first of all, that you can answer this question, and second of all, that it's so high. It's higher than I would have thought somehow. Okay, by the way, this zeta K here, this is the Riemann zeta function. Where is this? Why is the Riemann zeta function coming up? It's from Euler's product formula. Remember, Euler's product formula tells you that this zeta K inverse is exactly the product over all primes of this expression 1 minus P to the minus A. That's why it's coming up. So if I'm taking a product of all primes, I'm getting the zeta.
I have a question.
Yeah.
So this multiplication of these local pieces is based on this heuristic that the cyclicity for different P's are independent.
Yeah.
How surely it is established?
I mean, this is part of the work that they do. Yes, I mean, I don't know if it's sort of more broadly established, but absolutely, that's part of what is proved in their work.
Okay, thank you.
I mean, so yes, I mean, they're sort of establishing two things. One, that you do have this independence, but also that I can do this limit swapping. The limit swapping is highly non-trivial because, for a fixed n, if I consider all primes, for each prime, I have some sort of error term involving n that I need to kind of collectively sum together over all primes. And they do this analysis of what they call small primes, medium primes, and large primes. And what's incredible is that for large primes, so this big set of large primes, they really can kind of pull the various subtle estimates that they get together. But yes, both parts of the heuristics appear in their work.
I'm confused by annotation. What is this D in your?
Sorry, this is my horrible notation. D is just for the Bernoulli digraph. So this is the C is C for Kuntz, if you like. So this is the Kuntz probability for Bernoulli digraph. Yeah. Yes, it's not great notation that I just made up on the fly. All right. So here's what I was just saying about the Riemann zeta function. Okay, let's get to the other kinds of graphs. So the Erdős-Renyi ones, Erdős-Renyi, and the regular graphs. So here we have a similar statement for cyclicity of Syllov P groups. So first of all, there is a result about the asymptotic probability of getting any finite abelian group, G. It's a little more complicated in this case. So first of all, this infinite product involving P, it's slightly different, this normalizing factor. But also, we're not just dividing by the size of the automorphism group, we're dividing by this expression, which is the number of perfect pairings on G divided by the size of the automorphism group. Perfect pairing, I mean a symmetric bilinear form, considering these as Z modules, but that should be non-degenerate in a suitable sense. But this can actually be determined in certain cases. So, I mean, in all cases, there's a formula for what this is. You give me a P group, I can tell you what this NG is. In particular, if G is the cyclic group Z mod P to the NZ, then it's just P to the minus N. By the way, if it's not Z mod P to the NZ, but Z mod P to the Z to the N, you get P to the minus N times N plus 1 over 2. So what this is saying is that you're much more likely to get a cyclic group appearing as a Syllov P subgroup, as the K group of a random graph series algebra, than you are to get a sort of more complicated, as far as automorphism groups, non-cyclic. Okay. By the way, let me now briefly show you how you can deduce this non-singularity result from this statement of what we know the K0 to be. So if K1 is non-zero, that means I have this non-trivial torsion-free part of K0. So in particular, K0 is an infinite group. That means if I tensor by the p-adic integers, I still get an infinite group. Okay, why am I tensoring by the p-adic integer? If on, because it's infinite because I have this Z tensor ZP, which would just give me ZP, which is infinite. But if it's a finite group, on the other hand, tensoring with ZP just picks out the P Syllov subgroup. That's the relevance here. Okay, so now we do a little bit of estimating. So let's flip this around. So K1 not zero is a smaller event than K0 tensor ZP being infinite. So flipped around, K1 being 0 is a bigger event than the complement than K0 tensor ZP being finite. And what's the probability of, so not, as I say, this is just picking out the Syllov P subgroup. So what's the probability of it being finite? I just sum over all of the possibilities, so all of the finite P groups of being isomorphic G by Fatou's lemma, if that rings a bell for you. The integral of a limit is less than or equal to the limit of an integral, so I can do this swap, the cost of getting a greater than or equal to. And this limit here is this expression, this formula I had on the previous slide with this NG and the product of the primes. And what Nguyen and Wood show is that this formula actually does give you a probability distribution on finite abelian P groups. That's what I'm calling this mu G. So it sums up to 1. Okay, so the asymptotic probability of getting a trivial K1 group is 1. So getting some non-trivial is 0. Okay, so now let me just remind you where we are. This is the statement of what the Syllov P subgroup being a fixed cyclic group is for either the Erdős-Renyi graphs or the regular ones. Again, just doing this procedure of summing from n equals 0 to infinity, I get this expression. So this is the probability that the Syllov P subgroup is cyclic, some cyclic group. And now, okay, what about the final conclusion? So can we do this now, just multiply together for different primes P and get the answer for what getting something stably isomorphic to a Kuntz algebra? As far as the Erdős-Rényi graphs goes, that's what I mean by CE. So the Kunz probability for Erdős-Rényi graphs. Wood in a paper on the archive earlier this year, I mean, she did say that in forthcoming work, there will be such a computation. If we follow the heuristic argument, so this is the expression we should get. As I say, just multiply over all primes p of these of this expression. If you work it out, it turns out to be about 79%. In this case, about 79% of the time, you'll get something stably isomorphic to a Kunz algebra. Here I said supported by empirical evidence, which I will get to very shortly. Okay, so that's for the Erdős-Rényi ones. What about the regular ones? So here we still already have the question. We don't know theoretically what the distribution is if P is 2 or P divides R minus 1. So as for what that should be, all right, let's get to this empirical evidence. So my co-author Igor and I, we wrote some computer code in Python to generate some samples of these different kinds of random graphs, and we collected some k-theoretic data. I think that anyone who starts trying to compute k-theory of graph theory algebras, they quickly become acquainted with the Smith normal form. If you are unfamiliar, let me just tell you what it does. It's an algorithm with the input is an n by n integer valued matrix. And the output is this diagonalization. So you get UMV equals D, where U and V are invertible integer value matrix, and D is this diagonal integer valued matrix where the entries successively divide each other. In particular, the co-kernel of the matrix you started with is the co-kernel of the diagonal matrix D. So it's the direct sum of these cyclic groups determined by the DIs. Okay, so we use the Smith normal form to compute K0 and also compute the Syllov P subgroups. And then we just recorded a bunch of tallies of whether or not the graphs we generated were connected, whether we got non-trivial K1, whether or not we got cyclicity of K0 and K0 Syllov subgroups. And typically we did this for samples of 100,000. Did this for many different N's and R's and P and Q's. A lot of computing time went into it. Okay, so here is a one such graph that we generated. So this is a regular graph on 20 vertices, regularity degree 3. You can see here that a couple times there was a repeated edge, indeed. By the way, you may think that if n is large, the probability of getting a repeated edge goes to 0. That's not actually true, but it is bounded by n. Bounded as n varies, but that actually doesn't affect the analysis. I just thought I'd mention it since it does show up in the picture. Here's another graph. So this is one of these Bernoulli digraphs. So you can see that some of them are loops. Some, small c, but some of them have arrows from one to the other, some not. Okay, here I said n was in this picture, n is 11. I just did this to get a nice kind of visible picture. Typically, we did n is 100, really. And then, the picture quickly becomes this tangled, indistinguishable mess. But I just thought, we're at a graph algebras conference. It's nice to see some graphs. Okay, so here is some data. So these are these Bernoulli digraphs where n is either 50 or 100. And the edge probability is a half or third or a quarter. Okay, and at the bottom here, I have the limiting probabilities as n tends to infinity. So we would expect, as I said, most of the graphs to be connected. We would expect the probability that K1 is non-zero to be going to 0. By the way, so I said it's asymptotically 0, this non-triviality. In fact, Wood and her co-authors, they prove some quite more specific estimates. It goes to 0 like this. And here at the bottom, these are just so these are the CPs, the cyclicity probabilities for different primes here. And this is the product over all P of them. So it's the overall cyclicity probability, this is the Kunz probability. So you can see that, almost all of the graphs were connected. 6 of the graphs when we in the relatively sparser case of edge probability being a quarter were disconnected. But literally all of the graphs had trivial K1, okay? And all I want you to extract from this table of numbers is that these are the data values. They're quite close to the ones you would expect from the theory in the limiting. That's all I want you to know. So if you look at just this last row here, I mean, these numbers are quite close to the ones below it. All right, that's all I want you to notice. So on the other hand, remember I mentioned that this Erdos-Renyi result, the asymptotic probability of connectivity, it depends upon this asymptotic ability for asymptotic behavior of this omega. So just for comparison, I also did some different omegas. So let's maybe just look at the last two here. So if Q is log n over n, that means this omega is 0. Right, so it's not going up to infinity. It's in this intermediate case where it's going to C equals 0. So the connectivity probability we should expect is e to the minus 2 e to the minus 0. So e to the minus 2, in other words, which is about 13.6%. Okay, so here we get about 15.6% connectivity. I'm guessing as we took n to be larger and larger, we would get approaching this 13.6%. But also in this, even more dramatically. So here we have omega is minus a half log n. So it's negative. So it's going down to minus infinity. So here, absolutely none of the graphs were connected. They were all disconnected, which agrees with theory. And you can also see that the behavior of non-triviality of K1 is also quite different. So here, in these last two cases, with non-negligible probability, you can get a whole row of zeros even. So you can get some sinks and you can get some non-trivial kernel happening here. And indeed, you do get non-trivial kernel, a lot of it. And then you could almost also sort of see that the numbers are kind of drifting away from the limiting values covered in the previous cases. Okay, just for comparison, I want to include that. Here's a similar table of numbers for the Erdos-Renyi graphs. Again, you can see that virtually all of them are connected. Absolutely none of them had non-trivial K1. These cyclicity probabilities, so these are known from the theory. This is just like what I said is heuristically what you would expect and what Wood and Nguyen have announced that they have approved of in the works. Okay, and again, the point is that they're all very, very close to the values you would expect from theory. Okay, maybe those numbers are a bit to take in all at once. So here's some graphs, a different kind of graph. So these Bernoulli digraphs on 100 vertices with edge probability a quarter, and then I'm focusing on the Sylow 2 subgroups. So here the different possibilities. So Z mod, so the trivial Sylow 2 subgroup, Z mod 2Z, Z mod 4Z, Z mod 8Z, etc., etc., etc. I think from Z mod 2 to the 12Z continuing, we didn't observe any occurrences of those. So the green bars are the limiting distribution, just from the theory. The blue bars, which I hope you can see just behind them, are what we observed. And these kind of black error bars on top is just the confidence interval because because we're doing a statistical estimate based on a sample of the totality of graphs. Okay, but still, I mean, we have very, very close alignments to what you would expect in theory. Similar graph, just for the Erdos-Renyi graphs instead of the Bernoulli digraphs, we have again very, very close close matching to what we would expect from theory. And again, here is these regular graphs. So here, this was, n was 200. It really took a lot of time to compute these 100,000 samples of these graphs. And here, so R is 3, so R minus 1 is 2. So only P equals 2 is not covered by theory. All other odd primes are co-primed to R minus 1. So in particular, R is 5. And again, you can see that, the observed versus expected very, very closely matches. Okay, so what about some cases that aren't covered by theory? What about P equals 2? So here, N is 100, R is 9, and P equals 2. So when we were looking at, from the various data that we had, when we were looking at occurrences of cyclicity of still of two subgroups, most of the time, well, from the different cases we analyzed, the event still of two subgroup is cyclic tended to be concentrated on a single outcome, so on a single particular cyclic group. So here's one such instance of that happening. But it means, you know, some unusual behavior also happened. So here we have the same R, and again equals 2, but different N. And then we have a different distribution happening here. So instead of being concentrated on one particular still of cyclic group, we have kind of a spread. Well, what was really is still really puzzling to me is it's the same R, which is different N. So this is very different to what happens for the other P's. For other P's, you always get the same shape of distribution, but suddenly here we have a switch happening. But what you do have all of the time, seemingly all of the time, no matter what N is, if it's N is large, no matter what R is, the total mass of the bars is about the same all the time. So here's a table illustrating this. So here for various different values of R, these numbers in bold on the first row, these are the frequencies with which we observe the still of two subgroup to be cyclic. And you can see it's all the time about 0.42. Whatever R happened to be, independently of R, it's about 0.42. And here we have, so the other test we wanted to do was this heuristic argument. Is it true that K0 being cyclic, we just, you know, literally just multiply the cyclicity probabilities for the different primes? And this is also the case. You can see the products of the cyclicity probabilities very, very closely matches the overall cyclicity probability. But so the new thing is this distribution for P equals 2. All right, well, okay, where are these numbers coming from? What is the 0.42? Well, for the other unknown case, P, an odd prime dividing R minus 1, it turns out, it seems from the data that you have the same expression governing the distribution in this case. And the expression seems to be this. So in the cases we know from theory, the formula governing cyclicity was this, except starting from K equals 2. Right? So the difference here, the shift is we include the K equals 1 factor. That's what gives you these numbers. If you multiply this out with P equals 2, you get something close to this. And if you do it for different primes, you get these. So here I did, for example, R is 12. So R minus 1 is 11. So 11 is a prime dividing R minus 1. This is the frequency with which we observed cyclicity of the 11 still of subgroup. And this is what this expression computes to. It's very close all the time, very, very close. So that's what we suspect. These are this is some new distribution that we are seeing in these other cases. So that's by the way, I should say, so this paper will be on the archive sometime later this week. Also the data files, so you can see I'm not just telling you fairy tales there. And also the computer program will also be available if you want to play around with it yourself. So here's finally then the conjecture that we make. So in this case of the random R regular multigraphs, if P is in one of these cases not already covered by theory, so it's 2 or divides R minus 1, then we have what I was just saying, this similar sort of expression, just including the K equals 1 term. So if P equals 2, the percentage with which this happens is 42, approximate. And what about the overall Kuntz probability? Again, we expect it to just be the product over all primes. So with this extra term, just to take into account this different distribution for P dividing 2 or R minus 1. So in particular, if R is 1 more than a power of 2, then the only exceptional prime, the only one that's dividing 2 times R minus 1 is P equals 2. Okay, so in this case, all the other primes are covered by this. So in this case, we expect the Kuntz probability to be about 40%. Okay, so that's all I wanted to say. Thanks.
Thank you very much for the great talk. Now it's time for questions, remarks, comments. Also from people online.
Is this on? This on. Yeah, so I just have a couple of questions because I began to lose track near the end.
Yeah.
So these 40%, 42% things.
Yeah.
So the naive question, in the end, is the probability that you get a Kuntz algebra 85%, 40%, depends on how you count this.
Depends on how you construct the random graph model.
Mhm.
So maybe I should say, so the final answer to this question is for Bernoulli digraphs, 85%. For Eder-Shreni graphs, so the symmetric versions of Bernoulli digraphs, 79%. For these R regular multigraphs, we expect the answer to be about 40%. Although this is not proven yet, it's conjecture.
Okay, so a couple other questions that just come to mind. I don't know if these are interesting or not, but for any particular n getting the Kuntz algebra ON, did you have any sense of how those percentages divide up amongst?
That's an excellent question, and I don't know. I don't know. I mean, it would, I guess, require some analysis of the data that we didn't do to get an idea of what it should be, but I honestly, I don't know.
It is obvious that they are stably different when it has a ON and ON prime tensor compacts. They will be.
Oh, they're definitely not. It's the K0 group.
Yeah.
Okay. And so maybe, I'll ask you more later maybe, but the last question is, Blackadar calls Pn the analog of On, except swapping the degree of K theory.
I see.
Right, so K1 is finite cyclic and K0 is trivial. He calls it Pn.
Right.
So of course, these are probability 0 because they're K1 non-trivial.
Yeah.
But maybe the easiest, these aren't graph algebras, of course, because the K1 is not free.
Right.
But if you say, you could say, take a two graph that's like a product of the ON graph and something could be O infinite. It's not so hard to build something a little bit different that gives you that. Do you have any idea of what might happen, say, for finite? I don't know if you can do this with a finite two graph, but two graphs would give you a little bit more freedom in what kind of K group you look for.
Yeah, that's
but of course, there's some commutivity built into it, so it's a very different picture. But do you have any sense whether any of these methods might go through?
I don't at all, but it's a very reasonable suggestion. Yeah, it's not something I've thought about at all. So.
Yes, here's a question.
So the 42% is just a approximate number. It's not a exact number. Right?
Yeah, I mean, it's it's this expression with inputting p equals 2. I mean, I just
okay. Oh, this is the expression is the exact number.
Yes. It just, if you plug in p equals 2, it's about 0.419 blah 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 blah.
Okay, I see. Okay.
Do we have other questions?
I have a simple one about these Kuntz polygons. Could you go back to the slide?
Yeah, sure.
Yes. So if I understand you correctly, the multiplicity of the loops is always 1.
Yes.
Okay. And how about these m's? Do they have to be bigger than 1 or what?
There could be 1.
There could be 1.
Yeah.
And what will happen then with K groups?
Well, what you can say is that if they are pairwise co-prime, then you just get a Kuntz algebra. It's just the observation that Z mod M1Z plus Z mod M2Z is Z mod M1 M2Z if they're co-prime.
That will be a different graph presentation of just Kuntz algebra.
Yeah. Yes. Exactly. Okay.
Yeah. Thank you so much.
Yeah. I mean, honestly, I don't know if this particular graph has appeared in any way. I would be glad to know if anyone, but It's just a simple model I cooked up to get the right K theory.
But you said that you only get stable isomorphism. if
Yes.
The K theory is the same. So do you
Yes.
know something about the unit?
Well, yes, you do. I mean, the class of the unit in this is just, 1, 1, 1, 1, 1, 1, 1. So these are very far from being able to cover all isomorphism classes of finite graph algebras with trivial K1, because the class of the unit is essentially something very complicated and sort of built into the kind of complicated structure of the graph. So yes, it's almost never you get something actually isomorphic into one of these things.
So if the M's are pairwise co-prime, you get something stably isomorphic to the Kunz algebra.
Oh, in that case, you actually get isomorphic. You actually get isomorphic to the Kunz algebra. If M's are all co-prime, it's not just stable isomorphism. I think the class of the unit turns out to be just the one. So in that case, yes, in particular case. I mean, again, there are you can say when you do get, there is a class when you actually get isomorphism to these. And again, it's like, a Chinese remainder theorem type thing where you want to solve a certain set of simultaneous congruences. So you can kind of describe when you get something actually isomorphic to this, but it's a much narrower class.
All right, thanks. So since there are no more questions, let's thank the speaker again.
I have a question. Can you hear me?
Yes.
Yes. I was very curious about the corresponding question for shifts of finite type, classified up to flow equivalence, because we in a sense what we have here is that what corresponds to the Kunz algebras, those are the full shifts.
All right.
And then there's something called the Bowen-Franks invariant, which is a complete invariant for shifts of finite type up to flow equivalence, and it consists of the K group and also the sign of the determinant of the. There should be a parallel question, in symbolic dynamics. If you take a random graph and you create the random shift of finite type, then with what probability is it the same as a full shift? But then you need to know what is the sign of the determinant in probability. And I'm just wondering if there's any magic you could point to for that.
That's an excellent question. I mean, off the top of my head, I don't know the magic, but maybe it's out there. Yeah, that's a fantastic question.
I think this would interest dynamicists. And I Googled a little bit. There's a little bit of literature, but it's on higher dimensional, like ZD shift spaces. So that's different. I can send you a link.
Yeah, no, that would be great. Thanks. Yeah.
Thanks.
Thank you very much. Unfortunately, I can't see raised hands or anything. So if there are questions online, please just say something. Okay, I guess let's thank the speaker again. Thank you so much. The next talk starts at 11.